My presentation is over graphene. We will cover 7 different sections. Section 1, history. Section 2, the data involved. Section 3, production. Section 4, the uses. Section 5, the impact of the material. Section 6, recycling it. And Section 7, the footprint of the production. First is history. In 2004, there were 2 professors, Sir Andrei Guillaume and Sir Kostoya Novoselov, who discovered and isolated graphene for the first time. While it may have been looked at prior to this point, this is when it was actually officially discovered and documented. They went on to receive the Nobel Prize for Graphene in 2010. Some of the key points in history: 2004 was first isolated by Guillaume and Novoselov. 2009, it was used for transparent electrodes for displays in solar cells. 2010, it was experimented for touchscreens. As I said, Guillaume and Novoselov were awarded the Nobel Prize in 2010 as well. The 3D type printing of graphene was introduced in 2012. And graphene was introduced to mobile phone screens, batteries, and cooling in 2016. While later on in 2016 also it was used in cars and aircrafts. 2017 it was used for large solar cells. Now on to some data. Graphene, as most of you have probably never heard of it, is one of the newest and simplest nanostructures that we have found, as it is specifically only made of carbon, and it is in a hexagonal pattern like such as well on the screen now. It is only a single atom thick, so it has virtually no thickness at all. And there are many applications that this can be used for, because it transfers energy, transfers heat. It does really well in a lot of different applications. Some different data from graphene. Its modulus of elasticity is about 1 terapascal. Its shear modulus is about 1100 megapascals. Melting temperature between very, very high, at between 6,600 degrees Fahrenheit and 6,700-ish degrees Fahrenheit. As I said before, it's a hexagonal lattice that was on the last slide. It has a density of 2.3-ish grams per centimeter cubed, and it costs about 100,000 to 200,000 per kilogram. But as from the density, that is quite a lot of material. Production. One of the key ways that seems to have a very, very good chance of continuing is additive manufacturing, which is basically 3D printing. And this was found by researchers at the Massachusetts Institute of Technology. They could 3D print different parts and assemblies out of graphene. Production. There's many different researchers that have tried to figure out how to produce this, such as at Rutgers University. They use acid and oxidize the graphene to separate it and use by forcing oxygen between the layers. Then the acid is washed off and filtered out, and then they end up with layers of graphene. At California Institute of Technology, they found a way to produce it through CVD, which is chemical vapor deposition. For this, they heat methane to 420 degrees Celsius and use it to react with copper and nitrogen to form sheets of graphene. At Rice University, they found that using a really, really hot flash of electricity at 5,000 degrees Fahrenheit would melt down any items into gases, and then they could turn the carbon gases into graphene. This was primarily used with like trash. At Karlsruhe Institute of Technology, they produced it using carbon dioxide and hydrogen at extremely high temperatures. This, as I'll say later on, was primarily used to, it's very good for their carbon footprint because it gets rid of carbon dioxide. Uses. Some of the applications for graphene, as it is very versatile, were for things such as strain sensors, electromechanical systems, supercapacitors, and solar cells. Impact. The impact on the environment of graphene is that while it has been found that it can propagate through water extremely easily, it has not yet been found that will be detrimental to anything that it encounters. We have not learned enough to be sure if it could mess with the insides of a human body or the insides of a plant or animals. We haven't done enough research for it yet, as it's still relatively new material. So we're still trying to figure out, we're still doing research to see if it has any long-term effects on plants, animals, and humans and cells. While graphene is made of just carbon and humans are carbon-based, it still could end up not being safe for us. Such as the example of we need oxygen in order to breathe, but too much of it, or if it's too pure, it can kill us. Even though we're made of carbon, carbon may still hurt us. We still don't have enough information. We haven't done enough tests and trials. It'll be a few years before we have enough information. So there's two different sides that people have taken, which is pro-graphene and anti-graphene. On the side of pro-graphene, it's those who have argued that graphene is technically layers of graphite, and people have ingested graphite from pencils and ashes from fires for years, and we have not found any health issues that we've linked to it. On the side of anti-graphene, it is their primary stance is that we don't have enough research done to be sure. Recycling. So in order to recycle graphene, it is combined with zinc oxide, and the zinc oxide keeps the graphene layers from separating and from joining together and becoming graphite. It keeps it separated. So this can be done for about 5,000 cycles. And during those 5,000 cycles, 100% of the graphene can be maintained and reused. The footprint. For the footprint, so as I was talking about before, there are many ways that graphene is currently destroying more carbon dioxide than it is creating. So, take for example, if the cement industry would mix 0.1% of graphene into their cement, then it would cut their emissions by 1/3 of their carbon emissions. That is a large amount for just mixing that tiny amount of graphene in. It's also been found that graphene can help net methane out from the atmosphere when it's used correctly. And so a full-scale production has not yet taken place for graphene, but it's currently estimated that it would only take 1,000 liters per kilometer of graphene. And as stated before, graphene has a tiny density. It would give us a whole lot more graphene, even for that amount of water. And this is my bibliography.